1. Soil texture. Soil texture refers to the relative proportions of various types of soil particles. OR. It refers to the size of the soil particles. It is basic property of a soil, it can't be changed. In field condition, soil texture is generally determined by field method. Mechanical analysis of soil. It is the process of determining the amount of soil separates below 2 mm in diameter. It helps in determining soil textural classes. The International Puppet and Buyuko's hydrometer method are most common methods for mechanical analysis of soil separates. The International Puppet method is based on the principle of sedimentation. The textural class of soil is determined by triangular textural diagram. Textural classes. Total 12 textural classes but 3 main, i.e. sand, silt and clay. Sandy soil. Soil contains more than 85% sand. Silt soil, when more than 80% silt. Clay soil, when more than 40% clay. Clay soils have highest pore space than other. Classification of soil particles. Classification, according to ISSS, diameter in mm. Gravel, greater than 2.0. Coarse sand, 0, 2 to 2.0. Fine sand, 0.02 minus 0.2. Silt, 0.02 minus 0.002. Clay, less than 0.002. Loamy soil. These are best for agricultural production, especially sandy loam, because they retain more water and nutrients than sandy soils and have better drainage, aeration and tillage properties than clay soils. Suitable for most of crops. Heavy soils. The clay soil imparts cohesion and stickiness and fine texture to the soil and induces resistance to the passage of implements. In other words, it makes the soil heavy. These soils are suitable for cotton, rice, sorghum. Light soils. In comparison to clay soil, sandy soils offer little resistance to implements and called light soil. Example: light soils suitable for groundnut, potato, tobacco and legumes. Hence, the term heavy and light refers to the degree of resistance offered by soil to the passage of implements. But not to weight. In fact, the heavy soil weights less than an equal volume of the light soils. 2. Soil structure. Refers to the arrangement or grouping of primary soil particles viz. Sand, silt, clay and their aggregates into certain defined pattern is called soil structure. It refers to the physical shape of the soil aggregates. Soil structures can be changed, altered by agronomic practices, i.e. plowing, cultivating, drainage, liming and manuring. The primary particles sand, silt and clay usually occur grouped together in the form of aggregates. Natural aggregates are called beds. Clod. It is used for a coherent mass of soil broken into any shape by artificial means such as by tillage. Classification of soil structure. Structure is studied in the field under natural conditions and it is described under 3 categories. 1. Type. Shape or form and arrangement pattern of beds. 2. Class. Size of beds. 3. Grade. Degree of distinctness of beds. A. Types of soil structure. There are 4 principal forms of soil structure. Plate-like platy. The horizontal axis or dimensions are larger than the vertical axis. When the units, layers, are thick, they are called platy. When they are thin, then it is laminar. Platy structure is most noticeable in the surface layers of virgin soils but may be present in the subsoil. This type is inherited from the parent material, especially by the action of water or ice. 2. Prism-like. The vertical axis is more developed than horizontal, giving a pillar-like shape. Vary in length from 1 to 10 cm. Commonly occur in subsoil horizons of arid and semi-arid regions. When the tops are rounded, the structure is termed as columnar. When the tops are flat, plain, level and clear-cut, prismatic. 3. Block-like. All 3 dimensions are about the same size. Irregularly 6-faced with their 3 dimensions more or less equal. These types usually are confined to the subsoil and characteristics have much to do with soil drainage, aeration and root penetration. 4. Spheroidal, sphere-like. Rounded aggregates or pads not more than 2 cm in diameter, often in a loose condition in the A horizon. This is specific to surface soil, particularly high in organic matter, grassland soils. In this structure, infiltration, percolation, and aeration are not affected by wetting of soil. It is grouped into granular and crumbs. A. Granular. The aggregates of this group are usually termed as granular, which are relatively less porous. These are fine aggregates of soil, good for crop cultivation. B. Crumb. When granules are especially porous, known as crumb. It is most suitable for cultivation of crops. Hence, both granular and crumb structures are most favorable for plant growth. B. Classes of soil structure. It determined by size of beds. Each primary structural type of soil is differentiated into 5 size classes. These are 1. Very fine or very thin. 2. Fine or thin. 3. Medium. 4. Coarse or thick. 5. Very coarse or very thick. C. Grades of soil structure. Grades indicate the degree of distinctness and durability of the individual beds. It is determined by the stability of the aggregates. Grade of structure is influenced by the moisture content of the soil. Grade also depends on organic matter, texture etc. Factor affecting soil structure. Addition of organic matter increase the aggregate formation. Intensive cultivation destroy the soil structures. For good soil structure, tillage operation should be done at optimum moisture condition. Sodium ion destroy the soil structure due to deflocculation. Calcium ion destroy the soil structure due to flocculation. Mostly grasses and legume improve the granulation of soil. Roots and root hairs helps to develop crummy soil structure. 3. Soil density. It is measured by pulsometer. 2 types. A. Particle density. The weight of an individual soil particle per unit volume is called particle density, or it is the density of the oven-dried soil solids when air is excluded or excluding pore space. PD equals weight of soil solids divided by volume of soil solids. Particle density of mineral soils is 2.66 grams per cc or gram per cc. PD of organic soils 2.1 minus 2.4 grams per cc. PD of organic matter 1.1-1.4 grams per cc. PD, sometime also known as real, true density or gain density or absolute density. Particle density is lower when the organic matter added in soil. In presence of heavy minerals increase the particle density. In compare, water has density of 1 gram per cc. B. Bulk density, apparent density. It is the ratio of the weight of oven-dried soil to its bulk volume including pore space. BD equals weight of oven-dry soil divided by volume of oven-dry soil. It is also called the volume weight. It is determined by multiplying particle density by the volume of solids. 2.66 grams per cc by 0.5 cc equals 1.33 grams per square centimeter. Therefore, bulk density is generally half of particle density. Bulk density of mineral soils are 1.33 grams per cc. Bulk density of coarse textural, sandy, soils is 1.4 minus 1.75 grams per cc. Bulk density of fine textured soils, clay, is 1.1-1.4 grams per cc. Bulk density of organic matter is 0.5 grams per cc. Bulk density of compact subsoil is 2.0 grams per cc. Sandy soils have higher bulk density than clay. Addition of organic matter decreases bulk density. Compactness of soil increase bulk density. Soil with large pore space lower the bulk density. Tillage operations decrease bulk density. 4. Thermal conductivity. It is defined as amount of heat flowing in unit time through a unit cross section of soil. The thermal conductivity is high for sandy soils compared to clay soils. Soil moisture content increases, thermal conductivity also increases. Addition of organic matter in soil decrease thermal conductivity. Thermal conductivity decreases with increase in porosity. Tillage decreases thermal conductivity. 5. Soil temperature. Diurnal variation in soil temperature. Dry soil greater than moist soil. Loose soil greater than compact soil. Deep soil greater than shallow soil. Redox potential, oxide reduction potential of a system. It is denoted by AH. Measurable unit as MV. For well-drained, oxidized soil, plus 400 to plus 700 MV. Waterlogged, reduced soil, minus 250 to minus 350 MV. 7. Soil plasticity. Soil plasticity is determined by an apparatus called as liquid limit device. Soil containing greater than 15% clay exhibit plasticity. Range of moisture content in soil which exhibit plasticity is known as plasticity index or limit. Plasticity index given by Alteberg, 1911 also gave limits of soil. A. Lower plastic limit. Lowest moisture content at which soil can be deformed without cracking, and it is upper limit of moisture for tillage operations except rice. B. Upper limit or liquid limit. Higher moisture content which destroys soil aggregates or moisture at which cease to be plastic. Soil plasticity determined by apparatus, liquid limit devices. 8. Soil consistency. Resistance of soil at various moisture content to mechanical stress. Soil consistency order is dry soil, moist soil greater than wet soil, less resistant. 9. ODR, oxygen diffusion ratio, movement of O2 to plant roots. It measured by platinum wear electrode in soil, unit as GCM2, minutes. Range of ODR for crops, 22.9 times 10 to 8 to 39.5 x 10-8 grams per square centimeter per minute. For irrigated P, 39.5 gram per centimeter to minutes, highest ODR. For rice, 22.1 times 10-8 g per centimeter to minutes, lowest. 10. Soil color. Determined by Mulson color chart. A. Hue. It denotes the dominant spectral color, yellow, red, blue, brown. B. Value. Denotes the lightness and darkness of color. C. Chroma. Denotes purity of color. 11. Specific heat. Unit is calories, G. For water, 1. For soil, 0.2. For organic matter, 0.5. Note. The heat gain or loss by the soil is 5 times quicker than by the water because the specific heat of the soil is 0.2 and the specific heat of the water is 1.0 calories per gram. 12. Soil porosity, percent. Porosity equals 100, bulk density, particle density times 100. Or porosity equals 1 BD, PD, x 100. Porosity range, 30 to 60%. Medium to fine textured clay, soil, 40 to 60%. Sandy soils, 35 to 50%. Total number of pores, micropores, is found highest in clay soils. Large-sized pores, macropores, are found in sandy soils. Addition of organic matter increases the porosity of soil. Cropping reduces the pore space than outcropped soil. Crummy and granular, spheroids, soil structures have more porosity than other soil structure. Ideal ratio of micro to macro pores is 1:1.